Welcome to the second episode of Flat Earth Straw Men. A straw man is an intentionally misrepresented form of an interlocutor's argument, which is replaced for the actual argument because it's easier to defeat. Taking this approach in an argument is a fallacy called attacking a straw man. I will be doing the opposite, exposing the straw man to reveal how it differs critically from the real argument and producing support for the real argument. Another definition of straw man is a person regarded as having no substance or integrity. So the title of this series serves two purposes, as it highlights how little substance there is to the Flat Earth movement and the unprincipled charlatans who propagate it with dishonest tactics. Today we look again at my perspective and his explanation of flight paths. A link to his video is in the description below, but I will play the relevant parts of the 15-minute video here. We jump ahead to 15 seconds in.
Hi folks, my perspective here. This is a quick follow-up on my last video clip, Flat Earth, what time is it? In that video clip I dealt with flight paths. Let's have a look at that, right?
So this looks like a partial equirectangular projection, not a Mercator projection. Like all flat projections of a globe, it has distortions. MP is going to insist that the curved flight paths you see here, which represent the shortest distance on a sphere, should instead be drawn as straight lines.
So some people fail to get the point. This map is a flat planar surface. It's been extruded off a ball surface. This is what we are told. Therefore, it's a flat map. It's a flat planar surface. Those flight paths are curved. Those curved flight paths are on a flat map. So what some people are doing, they're imagining that the map is a ball. It's an illusion. It's just the way they work in the system. Everything is a mind game. Remember, this map is flat. So the shortest distance between Hong Kong and LAX is a straight line. The shortest distance between Hong Kong and JFK is a straight line. They just show you these curved flight paths, which are long flight paths. Do you understand? This is a flat map. These curved flight paths do not make this map a ball. It's a flat map.
He's obsessed with this flat map, which is an inaccurate representation of the globe. But he will never admit to that. He's going to use this map to attempt to defeat the globe. And that's his fatal flaw.
Part of the illusion. To illustrate the point, there's two islands, right? The shortest distance between these two islands is a straight line. So the yacht taking that straight line will travel a shorter distance. The yacht on the curved path, well, it's a longer path. So now I map this flat map onto a ball.
Here MP uses an example that is not the Earth, but an arbitrary and misleading map that he invented, which has this property. The straight line path that you see between these two islands on his flat map happens to be the same line as the Great Circle route between his two islands on the globe version of the map.
Does the long path now all of a sudden change? No. The curved path is still longer. Nothing's changed. It's just an illusion. If you turn the ball that way on top, it just looks shorter, but it's an illusion. That's the way they work in the system. Everything's an illusion. You have to look and think. Look, this is a flat map. It's a planar surface. It's been extruded off the so-called ball Earth. So if we look at the size of Greenland, right? If we look at it's called the Mercator map, right? If we look at the size.
Okay. So here MP shows how the equirectangular projection, which he mistakenly calls a Mercator map, can be derived from the globe. What MP will never do here is take a Great Circle route from the globe and show what happens to the points of that Great Circle route when the globe is subjected to an equirectangular projection. Skipping ahead a bit to, let's say, 310.
As I mentioned in that video clip, the shortest distance between these two dots is a straight line. If I map this planar surface, if I UV map it onto a ball, onto a sphere, the shortest distance would still be the straight line.
He's about to trick us again because this flat map that he's showing us, the straight line between these 2 points happens to be exactly the equator of the sphere that he makes. So obviously this straight line would appear straight on a globe and on a flat map because it happens to be a Great Circle route along the equator.
That's true. I'm going to prove it in another way. So the point was, the plane traveling on the red route was actually, its flight path was actually curved.
So here he very sneakily pretends to take the equirectangular projection and turn it into a sphere, but let's make some careful observations. The map is incomplete, and the process of turning it into a sphere is also incomplete. We're only seeing about 120 degrees of longitude. And also notice how the distortions that are part of an equirectangular projection, most of those distortions don't go away. So we know that he hasn't done a sufficient job of turning the projection back into the sphere.
its flight path was longer. The plane flying on the green route was a shorter route.
Here, MP is going to repeat the old canard about the straight line flight paths making perfect sense on a flat Earth map, and he's only going to show northern hemisphere ones. He would never show a southern hemisphere route because those do not look good on flat Earth maps. And notice he's using now a flat Earth map, the Gleason's or the azimuthal equidistant projection. This is a flat Earth map. The other flat maps he's shown are not flat Earth maps.
Route. And the routes all work out on a flat Earth map because airplanes fly in straight paths because it's about money. It's about money. They're not going to waste time flying around in circles. So some folks said, well, if I got a ball, right, and I got a piece of string and I pull the piece of string.
Okay. MP is going to become a sneaky snake oil salesman here. He's going to make good sense for about a minute straight, and then at the 5:15 mark, he's going to pull a bait and switch. So let's listen.
Whoa, whoa, whoa. Why are you using string? The string doesn't have a memory. You can twist the string and you're not going to measure anything. So it would be more appropriate to use a piece of wire. You stick a piece of wire through the ball, you bend it around the ball, right? That wire has a memory. Now you can measure on the ball with a piece of wire because it retains its shape.
You don't need to stick a wire all the way through the ball, and that's going to be part of the trick that he uses later. Really, all you need is 2 pins to indicate 2 locations on the surface of the Earth, and then you would take a wire or a string or whatever and loop it around those 2 pins. And the path that that string or wire takes would be the shortest distance between those 2 points. That's the important thing here.
Right? So let's have a look at it. If I take a piece of wire and I stick it right through the middle of a ball, straight through, I bend that wire around, right? And that's the flight path of that airplane. Now I can rotate that wire on its x-axis. I can spin it around the ball this way and that way. The distance is the same, right? I spin it around. I'm rotating that wire on its x-axis. I can rotate it on its y-axis. The distance is still the same. But if the flight path is not through the middle of the ball, it's not the same thing.
Okay. He just said if the flight path is not through the middle of the ball. And that's part of his trickery here. No flight path ever goes through the middle of the ball. All flight paths go across the surface of the ball. What he's trying to say here is that the 2 points, the end points of the path, do not lie 180 degrees opposite of one another. And so he's going to do a bit of trickery here. Listen.
Do that with a piece of wire through the ball. Now you cannot rotate that piece of wire. Because if you do, you'd have to rotate the wire through the ball. So the shortest distance would be that distance. Measuring it with a piece of string, it's just part of the illusion that people want to create.
Okay, so this distance here, this curved red line, that is still the shortest distance between the 2 endpoints. It also happens to be along a great circle route. All shortest distance or straight line flight paths on a globe are portions of great circle routes. And great circle routes have the property that their center, the center of the entire circle, is always the center of the sphere. NP is using the condition that the endpoints of the route are not 180 degrees apart from each other to imply that there's something different about this route. He insists on rotating the path around the physical wire stuck through the ball and not around the center of the ball itself. The physical wire stuck through the ball is a gimmick he uses. It is completely unnecessary for the real demonstration of shortest distance paths on a sphere. Notice how he never takes the globe model and projects it onto a flat map? He can't, because if he did, he would be betraying himself, because those curved lines on the sphere here, these great circle routes, would end up not being straight lines if they were to go into the southern hemisphere on a flat Earth map.
That's part of the trickery that they use to deceive people. It's part of the illusion. So the shortest distance then, if you push that piece of wire through the ball and you're not going through the middle of the ball, that would be the shortest distance between those 2 points.
Even if you stuck the wire through the center of the ball, but you put the pins here and here, the shortest distance between those 2 pins, if you continued it around, it would go through where you stuck the wire through. The remainder of the video, he uses additional poor examples, always in motion.
The shortest distance between one earlobe and the other earlobe would be...
He makes the same bad arguments with additional poor examples. The last 7 minutes of the video use some really dizzying animation to make arguments about speed, distance, and time zones. I don't know why he has all of this spinning going on. I might take these up in another video. I might not. Now it's time for my rebuttal. If I were to use a Mercator projection or an equirectangular projection and attempted to debunk the flat Earth with either of those, I would fail because those maps are not flat Earth maps. I would need to use the flat Earth map, which most flat Earthers agree is some variation on the Gleason model, or else I would be setting up a straw man, a false flat Earth map. MP has done exactly the same thing. He is not using an accurate globe map. He's using an inaccurate projection of the globe and attempting to debunk the globe with a bad map. A simple look at shortest distance paths on an accurate globe model, like Google Earth, will show that on a sphere, these lines are straight and are part of great circle routes. That is, for any 2 points on the path, the shortest distance between those 2 points is a subset of the great circle route, of which the entire path is itself a subset. When I place the center of the path in the center of the window, you see that the line appears straight, no matter what orientation I have the globe in. If I can get the center of the path in the center of the window, the line appears straight. When the center of the root is not in the center of the window, the line always appears curved. Now, when we look at the same flight path in Google Maps, which uses a flat projection of the globe, this same path from Hong Kong to Vancouver, that was what I had here, Hong Kong to Vancouver. This path appears curved. We can't overcome this distortion because we can't alter the projection being used by Google Maps. If we could alter the projection by rotating the map tiles individually and changing the center of the map to be the center of this route, I suspect we would find the path would appear as a straight line. However, that is outside of my technical expertise. What would the straight line on this Google map look like if we plotted it on a sphere? Here's the straight line between those 2 points. It would be difficult to do this well on a sphere because this straight line path goes pretty much only over water. There's no real landmarks here. But if you will permit me to choose 2 points at the same latitudes as Hong Kong and Vancouver, and the same number of degrees of longitude apart, but on a different part of the Earth, we'll be able to see what happens when you try to plot this straight line on a globe. Hong Kong is at about 22 degrees north, 114 degrees east, and Vancouver is at about 49 degrees north, 123 degrees west. I'm going to choose 2 new locations, one at 22 degrees north and one at 49 degrees north, and they're going to have 127 degrees of longitude between them. Basically what I'm going to do is I'm going to pick these pins up, spin the globe, and then put the pins back down. So, doing that, here's our new flight path. Our new flight path goes from near the Algerian-Mali border to somewhere in China, it looks like. Okay? And if I were to flick back and forth between these, you'd see that they look pretty much identical, almost identical. This distance is 6,483, and this distance is 6,372. So slight variation, but I was approximate with the latitude and longitude. I didn't include any minutes or seconds of latitude or longitude. Okay, but you can see that the contour looks almost the same and the distance is very close. So let's take that new flight path and plot the straight line again on Google Maps. Okay, so I've taken some time to identify some landmarks along this route, and I've created a quote-unquote straight line as best I could in Google Maps. There you go. That is pretty much that line. Okay. First, notice its distance, just shy of 7,200 miles, whereas this distance is under 6,500 miles. So we're adding almost 700 miles or so to the route. I think what this line ends up being on a globe is what's called a RUMB line, R-H-U-M-B, but I'm not entirely sure. Let's look at this on a globe map. This is what it looks like on a globe, and this is why I think I've created a RUM line, because it seems to be spiraling up towards the North Pole. Now, it's not easy to get this path to look straight. If I put the center of it in the center of the window, I can't get it to look straight. The only way I can get it to look straight, there we go. Let's tilt the Earth just a little bit. There we go. Now that line looks pretty straight. It kind of looks like a line of latitude. And that should signal something to you. The only line of latitude that is a great circle route is the equator. Following a line of latitude around the Earth will never give you the shortest distance between 2 points, unless those 2 points reside on the equator, because then the line of latitude you're following is the equator, and the equator is a great circle route. Here's a quick demonstration of the great circle route from 40 degrees north, 0 degrees latitude, to 40 degrees north, 120 degrees east latitude. That's this curved yellow line here. The line of latitude is 40. Okay? Watch what happens when I bring this curved yellow line and put it center, the center of the window. We get a great circle route. It's straight. In order to make 40 degrees north latitude look straight, I can't have it in the center. I have to have it tilted up like this, just like we had to do with this line. So I think that about does it for my perspective's attempt to disprove the globe with flight paths. Many flat earthers claim to understand the globe model, which is why they claim to be able to debunk it. But as MP has shown us, he either doesn't understand it, or he has to present a false version of it in order to debunk it. So next time, flat earthers, if you're going to try to debunk the globe model, argue against the real globe model. Don't set up a straw man, because I'll knock it down faster than you can. This is Jeff, realistically speaking.